My name is Kevin Pires. I am a subject matter expert with Exvo. Today, I will be talking about fiber optic theory. And so most of this conversation we're having is going to be revolved around single mode fiber, but we will be talking about different types of fibers as well. And so this is really more of an entry level discussion that we're having here today. And so, just kind of base it, kind of on that. So a lot of my presentation style is much more of a whiteboard type of material, along with being logged into actual equipment itself. And so I'm going to go ahead and start the session here. So really we'll be talking about, some of the basics of fiber. How fiber works, the different types of fibers that are out there from a very high level. And then we'll talk quite a bit about fiber connectors and then some of the critical parameters revolved around, testing different fiber optic systems. And so with that, we'll start with a little bit of a fiber refresher, right? And so fiber optic cable is, really quite prevalent today. It is probably one of the most common ways to deliver high-speed internets across the world. So you hear people talk a lot about wireless technologies and 5G and 100 gig and 400 gig. But what really enables us to utilize these types of higher speed technologies is really leveraging our fiber infrastructure that's in the ground out there today. And so from a very high level, looking at a piece of fiber. So when you look at a piece of fiber, this is essentially what we're looking at right here, right? So this is kind of a cross-section profile of a fiber here. And what we're looking at here is basically on the outside here, we have the coating itself, right? So we have the coating here on the outside. This could be 250 to 900 microns, depending on the type of fiber being deployed out there, right? And then right inside of that, we have the cladding. So this is the cladding right here. And so the cladding is also optical glass. Some people like to display it like it's a whole separate layer, but it's really all melted together with the core. It's just on the outer edge of the, the actual fiber itself. And so this could be, 100 microns, 200 microns, 150 microns. So there's different sizes here depending on again, your cable itself. And then we have the core itself. So the fiber core itself. The size of this fiber is a little exaggerated. It looks a little bit more like multi-mode fiber here. So, but this is the actual portion of the fiber that the signal travels down largely, is the actual core itself. So the core is kind of that optical conduit that we use to transport our signals, is essentially what it is, right? And so the two primary types of fibers that we have out there are going to be multi-mode fiber and single mode fiber. And so multi-mode fiber, we're typically looking at 50 to 62.5 micron, for multi-mode fiber. Human hair is probably around 100 microns or so. That gives you an idea of the size of the actual fiber itself, right? This is the fiber core itself. We see a lot of multi-mode fibers and enterprise deployments, some data centers, inner bay, inner rack. We still see some in some campus environments, a lot of legacy multi-mode fiber. But really, this is much more short reach type of deployments here for multi-mode fibers. Single mode fiber is what we see transporting most of our signals today, right? A lot of your backbone, your backhaul, even the last mile transport is single mode. And this is typically 8 to 10 microns. So a much smaller core. So it travels and propagates a single mode of light, where multi-mode fiber, you can have multiple modes of light, right? And so this is basically from a very, very high level, the two different types of fibers out there. And so down here on the chart, you can see some of the different attenuation profiles depending on the wavelength going down there. So for your single mode wavelengths, you're going to be seeing 1310, 1490, and 1550. And this is the loss per kilometer. So somewhere between 0.19 and 0.2 dB per kilometer at 1550 is what we're seeing. And then, of course, you see the multi-mode stuff down here just below it. And so these are the two types of fibers that we're seeing in the system heavily today. And typically, if you're looking at, let's say, jumpers, this is usually like a yellow jacket. Doesn't have to be. It could be different colors as well. But the most common is yellow. And then for multi-mode, you might see something that's either beige or orange if the jacket itself has any sort of color code to it. But again, they don't have to be yellow, to be single mode. In fact, we see a lot of blues and blacks these days as well. And so that's the actual fibers themselves. then we have to start thinking about the different connector types out there, right? And so for single mode connectors, this is what we're looking at here. Again, you see the yellow jacket. So there's different types of connectors. So this right here is a Frank Charlie. This is a Sam Charlie, and this is a Lima Charlie. So of course, those are just acronyms or nicknames. This is subscriber connector, a Lucent connector. And so these are different types of connectors in the system. Probably the two most common that we're seeing today are going to be your Sam Charlies and your LCs. The two most common. We're seeing a lot of LCs for much denser deployments. You know, if you really need that density, we see a lot in enterprise Ethernet circuits. The SC connectors or subscriber connector, we see a lot on, say, your transport and legacy systems as well. And then Frank Charlies are intermixed, right? We see these, throughout the networks and in different types of deployments. So this is a threaded keyed connector here, and these are pluggables. So you just, it has a key on it, you insert it, you plug it in. And so that's essentially what, what those different connectors are. And to kind of give you an idea of what some of them might look like. So I have a piece of fiber here. And this one here has an SC connector on there. So it has a 2.5 millimeter ferrule, where the LC actually has a 1.25 millimeter ferrule. So you see it's a little bit smaller. We'll come back to the color codes here in a second. But this is essentially what we're seeing for the two common, or the most common types of connectors. There's a lot of different types of connectors out there. STs, the old D4s, and there's a lot of different kinds, but these are probably the three most common that we see today. And of course, this is ever evolving. So that's the actual connector type, or the actual housing on it. We actually have two different types of end faces. And so we have APC, or angled physical contact, and UPC, ultra physical contact. So this will have a green housing, the APCs will, and then the UPCs will have a blue housing. And so, again, these are what we're typically seeing, in the network today, these types. And the difference between the two is APC has an angled cleave on there, and it's typically 8 degrees. And it changes the way that the reflection comes back. And so they have different reflection properties between the two. Where UPC has a flat polish. So it's a flat polish connector, right? So it's a flat polish connector. And the biggest differentiation between these two is APCs have less reflection. So they're not as noisy. And we'll talk about what reflection is a little bit more. But it has less reflection, the APC connectors do. And so, in fact, from this point, I can actually talk a little bit more about that. And so when we look at these different connectors of the fiber themselves, right, the two primary critical parameters that we're looking at when we're talking about fiber. So the two critical parameters that we're looking at, there's multiple parameters out there, but two of the most common that we're looking at is going to be loss, power, and reflection. Right? These are the two most common critical parameters we look at. There's other things as well, right? There's PMD, there's CDs, there's some advanced optic stuff. But for this particular session, I want to keep it very, very low level. So loss is pretty simple, right? Loss is what's the difference between the power going into my fiber and the power coming out the other side, right? This is loss. This is loss. So for example, if I have a transmitter that's sending out light at, we'll say, 10 dBm, which is a pretty powerful laser there. So this is the power level coming out. So this is the absolute power. I have 10 dBm of light coming out. On the receive side, coming back on the receive side, if I were to put a power meter on it, it'll say I have -5 dBm of power. And so if you do the math here, you can kind of extrapolate, okay, you know what? I have 15 dB of loss or attenuation. So dB is a relative measurement, dBm is an absolute measurement. So this is the amount of power, and this is the amount of attenuation. So that's the first thing that we talked about, is loss is basically attenuation going across the fiber. And what causes attenuation? Several things, right? Scattering, absorption, intrinsically within the glass, splices, connectors, pinches, distance, obviously. all of that stuff contributes to loss. And then, we'll talk about how we can measure some of that, some of those parameters as well. The other measurement is reflection. So reflection in the past wasn't something that a lot of folks, looked at, outside of the enterprise market. And reflection basically is light that bounces back towards a transmitter, right? It's light that bounces back towards a transmitter. That's basically what reflection is, from our perspective, right? And so that's light that comes back towards a transmitter. Reflection is over here. And so reflection is displayed in a negative value. And so, so some common values that you might see are going to be something like, say, neg 50 dB, neg 60 dB. So I'll explain what what these different values mean. But there's several different ones. Before I get to that, let's step back a little bit and talk a little bit more about the fiber theory portion of it. So essentially what I have here is I just did a quick little diagram of a piece of fiber. I use this diagram all the time for my training. So this, we'll call this standard single mode fiber, right? So this is just standard fiber. We'll say G.652, which is a very common type of glass out there. I'm not going to get too deep in the different classifications of fiber optics because there's a lot of them, but this one we'll just call G.652. So this is standard single mode fiber. So we're sitting 8.3 microns, 8 to 10 microns or whatever for single mode fiber. So depending on the type of glass what you have, right? And so that's basically the core size. So essentially what we do, and this is not exacting, so I'd have to look up the specs. I think it's 8.3 microns. That might be the mode field diameter. You have to apologize. I'll check on that and add a notation. But essentially what we do is we inject light at a specific angle and it reflects off of the cladding. So essentially, this middle section here, this is the fiber, and then wrapped around this is the cladding. This is all the cladding. Again, the cladding, and I say wrapped, it's really melted together. The cladding is different optical properties or different index of refraction, and so it maintains the signal within the core, and then it protects the core as well, right? Those are some of the functions of the cladding. And so what's happening here is we inject light at this very specific angle, and it has to hit a certain section of the glass, of the edge of the fiber to reflect. And so what I mean by this, so what do I mean by it needs to hit a certain piece of the glass to reflect? So if we were to look at, say, a surface of a pond, and I've drawn, and anybody who sat into my courses have seen this, little cheap illustration that I do. But essentially, you're standing on the edge of, say, a pond or a lake that's really, really smooth, right? You have the sun over here, and you have trees or whatever. If this is a very smooth surface of water, if you look at a specific angle towards the water, there's a section of this water that turns into a mirror finish. So you can see the trees and the sky and the sun, right? Because you have this reflection. If you look at a different angle, you're going to break the reflection, right? So if you look at a different angle, it's going to get into the water and then you'll see into the water. So that breaks reflection, right? This is basically what we call total internal reflection, right? So we call it, maintaining this perfect signal, we call total internal reflection. And so that's what we have when we're looking at this piece of fiber here. So back to this piece of fiber, this is the angle that we have to look at to get total internal reflection. This is basically how fiber works. And then of course, as the signal travels across the fiber, when it goes across a connector, you're going to have some sort of loss. When it goes across a splice, you're going to have some sort of loss. Absorption within the glass itself, scattering, is going to add to attenuation. So as the signal propagates, we're going to start attenuating and get loss. And for most standard single mode fiber at 1550, it's roughly 0.19 to 0.2 dB per kilometer, right, of loss. Roughly. There's different types of fiber. There's ultra low loss. So, this is just, kind of a baseline here. This is what's happening here. And of course, we have splices and connectors. So we need to understand the critical parameters around splices and connectors. And then using these two values here, or these two KPIs that we're looking at, these critical parameters, loss and reflection, we can start looking at different components. So we have, of course, splices. So anytime you splice a fiber, you're going to have some sort of attenuation. Typically, we're seeing anywhere between 0.1 to 0.25 dB typically at 1550. Again, these are just rough numbers. This will vary depending on your organization and what how they have their numbers established. So you really have to confirm what your SLAs are internally within your company. But from an industry perspective, most folks are within this range. Sometimes you have a little bit more room in there, right? And so that's the amount of loss. Now, for reflection to happen, we need a change in material type. So most reflection happens when there's a change in material type, meaning we're going from fiber, there's an air gap here, to air, back to fiber. So that change in material type causes reflection or light that comes back towards a transmitter. So if you're standing in front of a window and it's daylight outside and you're looking at a park, you can see your reflection in the window because what happens is and reflection is just, reflected light is all it is, right? So reflected colors that you can see. So, of the visible spectrum. This is, of course, we're dealing with 50 nanometers and in a whole different spectrum, but it's still kind of the same principle here, right? So that's reflection or light that comes back towards a transmitter, and we don't like this. We do not like this light coming back because this essentially can cause noise on the system and can affect what they call optical signal to noise ratio, which will directly affect your bit error rate, the quality of your bit error rate, right? As one of the tests that can possibly be done on the fiber. So anytime there's a change in material type, you have the chance of higher reflection. There's going to be reflection intrinsically within the glass, right? There's going to be reflection intrinsically within the glass. But after a certain distance, it kind of just flattens out, right? So it might start at, say, 80 dB of optical return loss, which is span reflection. And as the fiber gets longer and longer, it generally starts to flatten out somewhere in the mid-30s up until infinity. So intrinsically from the glass, you shouldn't get any worse than, say, the mid-30s or in that range. What brings this number down is dirty connectors. So connectors are what we call reflection. So the two critical parameters, again, we're looking at is loss and reflection. Reflection is light that comes back towards a transmitter. That's this stuff here. And it's measured in a negative value. It's measured in a negative value. And some of the values that I had up here earlier that we were looking at were things like, neg 50, neg 60 dB in that range. So I'll start to explain where these numbers come into place. So if I have an open UPC connector, so let's say that this connector here is closed up. So I have a closed UPC, a flat cleave connector. If I were to apply a source to this connector and measure the reflection coming back, roughly this is going to be about minus 14.7 dB. This is an open flat end face. So this is an open flat end. It's 14.7. If I mate together two APC connectors, so this is an APC to an APC, right? It's essentially what this is, a blue connector to a blue connector. Attenuation-wise or loss-wise, so again, our two critical parameters, loss and ORL. And reflection. In this case, we're going to talk about reflection. So these are our two critical parameters that we're looking at. For most connectors in the industry, it's usually 0.5 dB or better. Typical is about 0.2. That's typical. And for both of these connectors, they're the same. UPC connectors have a flat 90-degree cleave. APC connectors, again, have an 8-degree angle. So they have a different end face type. Reflection-wise, a UPC connector has usually 50 to 55 dB of reflection. An APC connector has usually minus 60, minus 65 or better. And so you notice these are negative values. If you disregard the negative, the higher the number, the less reflection or the better off you are. So a 40 is worse than a 50. A neg 40 is worse than a neg 50. So we want a higher number if you disregard the negative. We want a higher number. And so that's what happens here. And so APC connectors have less reflection or less noise profile. And so they were used heavily in analog video systems and are the standardized connectors for APC fibers. And so any organization that came from the RF analog video world, like a cable TV company, they've been using these APC connectors for a very long time. They have the cleaved angles. If you came from more of a telecom environment or some of the data center environments, you're mostly from a UPC or flat cleave connection. So once you start doing amplification, like with ROADMs and with analog video or with very long haul transport, then going to APC starts to be much more advantageous because minus 65 dB is a better reflection profile, right? And so we have less noise. We have more margin, for reflection there. And why is APC better? It's really quite simple pool table physics. And I have quite of a mess. I have a bit of a mess here. Let me see if I can clean it up a little bit. So I'm drawing all over this board here. But essentially what's happening with these, these connectors, whether it's, UPC or APC here, is we are reflecting light back, right? So we're reflecting light back. And I call this pool table physics. So as my signal comes in and it bounces or reflects off of the cladding and it hits that 90-degree angle, it's going to come back at the same angle, right? Like high school geometry, the angle of the angle of incidence equals the angle of reflection or something like that, right? And so it comes back at the same angle, which means our reflection is also maintaining total internal reflection. And we don't want to do that. We don't want this signal coming back. We want to break it. So what we do with APC connectors is now that because it has an 8-degree cleave, when you bounce or reflect the light back, it's going to change the angle. And it's going to miss total internal reflection and then bleed off into the cladding or run along the edge. But it breaks reflection. So it doesn't come back. So this is why we have less reflection. Again, pool table physics. If I bounce a tennis ball off the floor and it hits my flat wall, it's going to bounce back at the same angle and then I'll catch it. But if it's an 8-degree wall, then it's not going to come back at the same angle. And so we kind of break our reflection, right? That's what's happening there. And the reason why reflection is really much more prevalent in a high power system, if you think about a connector here, like this connector here, if you think about it, this flat cleaved connector, and this one's got a bit of a mode field diameter or core mismatch or something going on here. But essentially, what's happening here is, and one way I like to draw it is I talk about water pressure. And so I'm gonna move over here to a blank slate here. So let's say that I have a garden hose, right? So I have this garden hose, and I have a wall. So I have this wall. As I turn on my water pressure, if it's really low water pressure, it's gonna hit this wall and just run down the wall, right? So very low pressure. Pressure or PSI in this example is power. As I increase my power, so now it's coming out much faster. So I'm now amplifying my system. What's gonna happen? It's gonna hit this wall and it's gonna reflect back into my face. And this reflection coming back is noise, right? So as you increase your power output of your laser, reflection becomes much more critical to keep an eye on. And most reflection issues in a system comes from a connector, So understanding these different connectors is important. And understanding what the parameters are for these connectors is also important. So understanding the specs of a connector, right? And so going back down to here, splices, 0.1 to 0.25, connectors, again, this is, can be anywhere, 0.2 is typical to 0.5 dB or better at 1550. There's some margin there. Again, this will vary with companies. And reflection-wise, at spec, this is what we see for APC. And then this is what we see for UPC, right? It's more of a neg 55 these days. But, you'll see some specs, especially some of the older ones that say neg 50 to neg 55. But this is roughly the values here, right? Most APC connectors I see well above 60. And sometimes they get, way up over 70, 5 dB or so, which barely is any reflection at all. Starting to get into the reflection of the glass at that point. But this is basically from a very high level what fiber is, right? How it works. So how the signal propagates down the fiber. We bounce off of the cladding or reflect off of the cladding with total internal reflection. Anytime there's a change in material type, we're going to have reflection, and that reflection is going to cause noise, right? And of course, we're also going to have attenuation as we go across those different connectors and those different splices, and we want to minimize that as much as possible. And so that's what we're looking at when we're talking about these different types of connector end faces here. And when it comes to loss, you know, the thing about loss is that every, you know, so if you have 3 dB of loss, power loss, this is 50% reduction, right? It's 50% reduction. So you can see here as we attenuate the signal. So at 0 loss, of course, we have 100% of the signal. We get down to 3 dB of loss here, and then all of a sudden we're down 50% of our power, right? But if you notice, every 3 dB, we go down another 50%. Every 3 dB, another 50%. And so you can kind of see how it just kind of scales. So if you have a system that has, say, 20 dB of attenuation, so you have 20 dB of loss going across your fiber span, you only have about 1% of the remaining power of the original signal. So that just tells you how much light or how much attenuation we have going across the fiber as you keep going down the system. And so from a very, very high level, I don't want to get too deep into it, that's essentially what, you know, from very simple Fiber 101. Understanding how fiber works and propagates, the different types of fiber. Again, I didn't want to get too detailed into it. I didn't want to get into too specific of values in some of them. I just want you to really conceptually understand, you know, what's going on here and, you know, the different types of fibers that we're dealing with. And so from this point, you know, understanding, again, the different types of connectors and stuff really does become important, because if you start looking at systems that have different types of connectors, right? Because, you know, we talked about these 2 different kinds of connectors out here. So the green connector here, this is APC, or angled physical contact. It'll be hard to see here, but there is an angled or 8-degree cleave on this connection here. So you must plug a green into a green. You should never plug it into a blue connector. You can damage it, all right? So that's very important to understand. And then, of course, you have the UPC here, right? The UPC. And so if you wanted to inspect fiber, so what I'm going to do here real quick is I have a unit set over here. So I have the FIP435B here. So this is a wireless inspection probe. So I've turned it on, and I'm going to connect it to one of my test sets. I can connect this to a phone. I can connect this to another Expo test set. I can connect it to a laptop. But essentially what I'm going to do here is I'm going to go ahead and let me turn on my VNC here so you can see it. So I'm logged into a piece of test equipment here. So I'm logged into an FTB1. And so you'll see where I have a wireless connection here. So I'm just going to go ahead and just hit connect. So we're connecting to this FIP. And I have this one already set for single mode. And it's a little hard to see there on that screen. I can increase this slightly, I think. But anyways, essentially what I'm going to do here is I have this UPC connector. And so I haven't cleaned it or anything. So there's different tips on these fiber inspection probes. And I have a different video that talks about that. This is the bulkhead tip. So this is what allows you to look at a bulkhead. I also like to use it for jumpers, so I don't have to change the tip. There's a different tip for a jumper. What I like to do is I just put a bulkhead on the end of this, and then use the bulkhead adapter here. And then essentially this is autofocus, auto center, you know, auto, all of that stuff. So I'll just plug it in and let it go. And we'll see how it auto centers and auto focuses here. There it is. And so here's our fiber. So this section here is the core zone, right here in the middle. Wrapped around that is a cladding zone. So this is the cladding. This is the adhesive zone. We've called it the adhesive zone because sometimes you'll see a dark crescent shape around here. That could be the epoxy leaking out. It's smooth flat, it's polished flat rather. So we allow a little bit extra contamination here, knowing that there's a chance there might be some adhesive that's showing through. It's almost like if you're woodworking, you have a glue line, but if you sand it flat, you can still see the glue line, but you can't feel it. So that's essentially what's happening here. This is the contact zone. So this section right here, this entire outer ring is where the fiber touches. Everything outside of this rounds off. So out here is the no contact zone. There's nothing out here touching. This is a section that touches here. And so anything that's green, well, it passes the parameters for that particular spec. Anything that's red fails. So we obviously have some reds in there. So this is a pretty dirty connector here. So what I can do here is I can, and you see we got a fail here on our LED. What I can do here is I can take this off. And there's different ways to clean, right? I have a one click here. I have a dry tissue. I have a Cleatop. I have some fiber cleaning solution here. And so I prefer a dry tissue with a wet solution using something called hybrid, right? So the one click works really well. Is really more designed for cleaning bulkheads. You can plug in this adapter on the end here to clean the jumpers. And so you'll see, we'll get a really quick look to see what this looks like with that quick little Cleatop cleaning. So it got it pretty clean, much cleaner than it was before. But it's a dry method of cleaning. So if there's any oils on there, it's still going to be contaminated with the oils. We just don't see it. So now we have a pass all of a sudden here, right? So I prefer a wet to dry method, right? And so using the dry tissues here, I will take some sort of alcohol solution here and I'll spray, of course, I'll get me some fresh tissue there. I'll spray a portion of that with the wet solution. And then I will start into the wet and then pull into the dry. Start in the wet, pull into the dry. And I'll usually do it 3 times. And then I'll re-inspect the fiber to see how it looks contamination wise, right? And so that's how I typically do it for fiber cleaning. And of course, again, there's different types of methods out there, but that's what I use. The thing about APC is it's got an 8-degree angle on there. And so what I normally do is I put my thumb on the key and that kind of orients me where I'm at. And so the 8-degree is right here. So I'll kind of hold it and pull it down. Hold it, pull it down. So that's how I clean an APC connector as well. And so it is, having really good cleaning method is incredibly important because as we talked about with reflection, that's one of the main contributors of noise in a system is connector reflection. So one thing I wanted to show is what cleaning a connector looks like with an OTDR trace. So I'm going to go ahead and fire up my FIP 435 here, so my inspection probe. I'm going to go ahead and fire that up real quick and let it launch. And then at the same time, I'm going to bring this fiber into the scene here. So essentially, this is a Sam Charlie SC UPC connector. I think it's about 150 meters out from my launch. We'll find out here in a second, right? Over here in the top left, we have my FTB1 along with the FTB X730C OTDR. That's this top module here. So I'm going to go ahead and fire up the OTDR. I could have also used IOLM as well. In this example, I use an OTDR. And so I'm going to go ahead and shoot one quick trace. So I'm going to do a trace, and I have a whole separate video on how to set up an OTDR. So I already have the parameters all set up just for expedience here. So I'm going to use 30 nanoseconds for 10 seconds, only at 1550. So I'm going to start a quick test here. We're going to let it run for 10 seconds at 1550. And this right here is the connector that we're looking for right here. So you see that tall spike here? On an OTDR, these tall spikes are basically reflections. So anywhere we see a tall spike, that's reflection. So this is distance, this is power. So as we're seeing attenuation going across, we see that. So if I were to click on this event and zoom into it, this is my connector. That's this connector right here. It's a UPC connector. And if you look at it, it's kind of hard to see here, but it's 0.07 dB of loss, so not a lot of loss, neg 44 dB of reflection. Not terrible, but not great, right? Not great. The taller this spike, the worse the reflection is. So I'm going to take it apart here real quick. I'm going to take it apart. I'm going to fire up Connector Max. Fire this back up because I turned it off after, showing it earlier, showing the fiber cleaning. But I really wanted to finish with this because I think it's a strong finish. So I'm going to go ahead and connect to the wireless inspection probe. Again, I can use my phone as well, but in this case, I'll just connect to it here. And I already have a bulkhead on here. And so as we mentioned before, how to do that. So I'm going to go ahead, once this is blinking blue, it's ready to do analysis. So I'm going to plug it in, let it do its auto center, autofocus, and it should be pretty contaminated. Look at that. That's very contaminated there. So let it do its thing. And we're losing a little bit of resolution going across VNC here. But essentially, obviously, we have a bit of a train wreck here. So if I double click on it, you can kind of see. So anytime you see this rounding, almost like this cratery effect of debris, how it pushes itself out. This is the contact zone, so you can see how all the oils push themselves out to the end. This means that there's cross-contamination. It's been plugged in dirty. So if I were to unplug this real quick and just take, say, my one click here, take my one click, plug it in, and of course a one click's never just one click, right? I did a couple of clicks there. And if I were to re-inspect this, it should look quite a bit better. It's probably still a little oily. I did get a little bit of lint on there that you could see, but it is significantly better, right? But that lint's far enough out on the edge in the right zone that the software, based on the specifications, is all right with it. But if I take this, I didn't clean the jumper. If I plug this back in, terminate it, unplug it, and then re-inspect it, what do we expect to see here? So that is trying to re-evaluate it. And it'll recenter here in a second. It'll snap to the center. Just give it a second here. There we go. Now, this is cross-contamination. See how all this contamination is just spread out in a nice cratering effect? You know, it's almost like putting a dab of oil on your finger and then touching the two fingers together and letting go, and you get cross-contamination. So it is very important to clean both sides of the connector. And again, like before, I prefer to use the wet-dry method. In this situation here, I'm just going to do a quick cleaning with a clay top, with one click on this side and a clay top on this side, which are probably the most common methods of cleaning that I see. I'll do a quick cleaning there. Both of these, and just terminate them. And remember, our value was neg 44 before it had that big spike. Let's see what it looks like with the OTDR now. So I'm gonna go back to the OTDR. Here's that big spike here, so you can kind of get a reference. I'm gonna start another test. And we made it run through. Oops, I'm gonna do that. Hit don't save. So now we're acquiring another test, and you see the reflection is not as tall. So we have a nice cleaner connection. We still have low loss going across here. See how pretty flat that is? And so if I were to zoom back out and go back to that connector here, because they changed on me, go back to it. Now we're at neg 51 dB. So we're at now neg 51 dB. So it's significantly better, right? It's significantly better. And the loss is improved slightly as well. It was already low. And so just by that quick cleaning, we are able to confirm that we have a much better connection here, reflection and loss wise. And so that's, kind of how important it is. And so I kind of wanted to end with that because I think that's really a powerful statement to kind of show the importance of cleaning connectors, to help you better understand, how fiber works, and then some of the issues that we have, kind of revolved around fiber itself. But yeah, that's pretty much it in a nutshell. My name is Kevin Pearies with Exfo. Thank you very much.